evaluate the partition function, that's the denominator, z of x bar w is sum over y bar exponential of sum over j, wj, fj, x bar, y bar. Okay. And I can use my same notation as before. So this is the sum over I of gi of yi minus 1 yi. Because inside here, this capital Fj is the sum over I, and then I swapped the sum over j and the sum over I. And so this whole thing is the sum over y bar, and this is so now here this is an exponential of a sum. So the exponential of a sum is the product of the exponentials. If I move the exponential inside the sum. So it's product over i's of the exponential of gi of yi minus 1 yi. So this still looks pretty intractable. It's a sum of products. But I'm going to come up with some tricks. So so for t equals 1 to t equals n plus 1, so I'm using t as an alternative to I. So I ranges over the positions in the sequence, and t is going to range over the positions in the sequence also. I'm going to define m sub t of uv is the exponential of gt of uv. So remember I said my g function, there's a different g function for each I, or different g function for each t, but each of those g functions I can represent them as a matrix, an m by m matrix. So I'm doing the same thing here, just with slightly different notation. So this capital M sub t is going to be the matrix that represents the exponential of the g function. So these are really the same matrices I had before. I'm just taking the exponential of each entry in the matrix. Okay. And now, okay, so notice that m1 of u and v is defined only for u equals start. Because m1 of uv, well then u would be y0, and y0 is always start. And similarly, m n plus 1 of uv is defined only for v equals end. Because y n plus 1 is the label of the position after the end of the sequence, and that label is frozen to be end. Okay, so now let's consider doing some tricks with these matrices. Okay, so define M12 will be the matrix M1 times the matrix M2, matrix multiplication. So consider M12 of start and W. So this is a single entry. This is a single entry in the M12 matrix. So it's the I have a one square matrix and I'm multiplying it by another square matrix, and so I take one row here and then I multiply it by one column here, and that becomes the entry. So this would be start, and then this would be W. So that's just the sum over V of M1 of start V times M2 of VW. So this is just a definition of matrix multiplication. But this is the sum over V of the exponential of G1 of start V plus G2 of VW. So notice this is starting to look a little bit like what we want, because what we want is the sum over the y sequence of the product of exponentials, or the exponential of the sum. And here I have, it's not the sum over the whole y sequence, but it's a sum over it's a sum over a single v of the sum of the g values. So I can call this sum over y1. So if I calculate the matrix M12 and I look at its entry start W, that's going to be the sum over all y1 of exponential of g1 start y1 plus g2 of y1w. And so I can continue. So M1, 2, 3. So now I'm multiplying together M1 and M2 and M3. And I look at the start W entry in that, and it's going to be the sum over y2 of M12 start y2 times M3 of y2w. Which is the sum over y2 of, so now I'm going to plug in here what I just learned from here. So sum over y2, sum over y1 of exponential of g1 start y1 plus g2 y1 y2 and then I have, here I have m3 of y2w, so that is the exponential of g3 of y2w. So this is sum over y1 and y2 of exponential of g1 start y1 plus g2 y1 y2 plus g3 y2w. So by multiplying three matrices together, I've got a nested sum. So the outer sum is sum over y2, the inner sum is sum over y1. But that's just what I mean by a double sum over y1 and y2. And I have, inside the sum, I have the exponential of the g1 function plus the g2 function plus the g3 function. And so by multiplying three matrices together, I'm summing over all y1, y2. And if I and I can continue, and so I can eventually, if I've multiplied together all the matrices 1, 2, 3 up to n plus 1, and I can look at the start end entry of this combined matrix. And it's going to be the sum over y1 up to yn of the exponential of g1 of start y1 plus g2 y1 y2 plus g3 y2 y3 so on up to gn plus 1 of yn and end. And this is exactly the thing that I wanted to evaluate for the partition function. It's the sum over all possible assignments for the individual yi of the numerator for those particular yi. And so this algorithm, the previous algorithm has a name, the Viterbi algorithm, and it has a category of algorithms that it falls into. It's dynamic programming. And this algorithm, well, the way I've presented it, it's a matrix multiplication algorithm. So to implement it, all you need to do is create these M matrices and then multiply them all together. So that's computationally very easy. It's actually a special case of a more general class of algorithms called forward-backward algorithms. And I guess I'm not going to try to explain why this is called a forward-backward algorithm. But if you're familiar with hidden Markov models, they have forward-backward algorithms also. And what I'm explaining here is just a very narrow special case that solves exactly the problem we're interested in solving here. But this is still general for linear chain conditional random fields. Here. Okay. So those are the two important algorithms that we need if we want to use conditional random fields. Now we need to talk about training conditional random fields. Any questions on that? So and going to use stochastic gradient descent or ascent for maximization. So the model is that log p of y given xw is, so we have the normalization constant, and then exp sum over j fj xy. And so to do stochastic gradient, we need to evaluate the derivative of this. So this is the log probability, so that's the objective function to maximize for a single training example. So we want to evaluate its derivative. And so d by dwj of log p is, okay, sorry. So this is the p function. So the log p function will be the log of this. And what I want to do now is the derivative of the log p function. And so the log of this is the log of the numerator minus the log of the denominator. So it's d by dwj of sum over j, wj, fj, xy minus d by dwj of z of xw. What's this first part of the derivative up here? Something very simple. Is that?
The GI.
The f. It's just fj, big fj.
Oh, the derivative.
Yeah. I'm back to using the big fj's, the high-level feature functions. So this is fj of xy minus d by dwj of this z function. And okay, so this part here is going to be, it's going to work out, this is going to work out to be something very elegant, but it takes a few lines to work out what it is.
Sorry.
Yes?
Am I missing something? Maybe it's being late in the day. Where did your summation go for the first part?
Okay, good question. So this is a partial derivative with respect to parameter number j. And this is a sum of,
Right. So all the other ones disappear.
all the other ones disappear. It's a linear function of wj, so all the other ones disappear. Yeah. So, okay. I'm going to just get some room. So d by dwj of log p is fj of xy minus d by dwj of z and d by dwj of z is minus d by dwj of log z. So this is 1 over z d by dwj of z. And the okay, I'm just looking at my own notes and trying to figure out how that went. Okay, so z is a summation. So this is 1 over z sum over y prime. This is actually a minus here. Is that? Okay, no. The minus is here, but not here. So 1 over z, and then z is a summation, and so I'm going to bring the derivative inside the summation. So sum over y prime, d by dwj, and then inside here we have an exponential over sum over j prime, wj prime, f j prime of x and y prime. So really the only thing I've done here is write out what z is, which is the sum of the numerator. So here's the numerator. But then the derivative of an exponential is the exponential times the derivative of what's inside the exponential. So we have 1 over z sum over y prime, and then the exponential, which is this sum over j prime, wj prime, fj prime of x, y prime. And the derivative inside here, again, is just w of j prime. So the derivative with respect to wj of this sum is going to be fj prime. Because we just, for the derivative, we just pick out whichever j we're talking about. Times fj of x and y prime. What? It's actually, no, it can't, because what I can do is bring the z inside the sum, but I can't, but I don't think I can cancel it out. So this is, I'm going to write it like this, sum over y prime, and then so the parentheses here are like this. So I'm going to write fj of x and y prime. So I'm just moving this first. And then I'm going to move the z inside. And so z and exp sum over j prime, wj prime, fj prime, x, y prime. So here I just swapped the order of these two things in the sum and moved the z inside. And now comes the interesting part. So I can recognize this as being something well known. What is this? Something we've seen. It's p of y prime given x. It's p of y prime given x. And also w. But the w is not important now. So now if I go back to here, the d by dwj of d by dwj of log p is fj of xy minus the expected value, so this is an expectation, of fj of x y prime, where y prime follows the distribution p of y prime given x and w. So, see, this is the definition of an expectation. It's a weighted average of the fj values for all y primes, with each y prime weighted by the probability of that y prime. So it's the expected value of fj, x, and y prime. So what it's saying is that the observed value of fj, x, y for the training example xy has to equal the expected value of this same feature function, where the y primes are all possible labels weighted according to their probabilities. So this result is a generalization of the result that I had for logistic regression, that the expected value of each feature using the, actually no, it's not a generalization, it's related to the result I had for logistic regression of the empirical average being equal to the average using the predictions from the model. And here it's saying that for each individual training example xy, if I take the it's saying that this difference is the derivative. And then if I set the derivative to 0, if I set the derivative to 0, I'd equal that the empirical value equals the expected value. But I don't want to set the derivative equal to 0 for a single training example. I'd only want to set the derivative equal to 0 for the derivative of the whole training set, which would be the sum of the derivatives for each training example. And when I did that, then I'd get that the sum of these equals the sum of these. And I guess the expectation of an expectation is an expectation. So I would get the generalization of the result that I had for logistic regression. But so what this is a generalization of the simple formula I had for the derivative for a when I'm doing stochastic gradient update of a single feature for a single example. And notice that if I have a feature function, okay, so we can ask the question, so when does d by dwj log p equal 0. Because if the derivative equals 0, then we can skip doing any update for this feature. And if we have tens of thousands of features, then we don't want to have to update every feature for each training example. We'd like to be able to skip doing most updates for most training examples. And so what's the answer? Can anybody look at this and figure out an elegant way of saying the answer? When is this derivative guaranteed to equal 0? Okay, so you might think, well, what if fj of xy equals 0? Does the derivative equal to 0? Well, no. Because this part of the derivative will be 0, but then this part might be non-zero. So, but under what circumstances will both parts of the derivative equal 0? No. So, if fj of x y prime equals 0 for all y prime. So so here we're taking the expected value of fj of xy where over all possible y's. But if the thing that we're taking the expectation of is uniformly 0, then its expectation is going to be 0 also. And if fj of xy prime equals 0 for all y prime, well, it also equals 0 for this particular y. So this is a useful, sufficient condition for the derivative being 0. And so we have many feature functions. So so often fj of x and y is some function a of x times indicator y equals v. So remember how we translate regular features into feature functions. So the regular feature is a of x, and then we make a separate feature function for each possible value of the label y. So we have the feature function of this form. And then this is going to equal 0 for all y if a of x equals 0. So then a of x equals 0 implies f j x y equals 0 for all y. So we actually get pretty much the same savings from sparsity with a log linear model that we do with logistic regression, because anytime we have a standard feature a of x equals 0, then we don't need to do any update of the weights for all the corresponding feature functions. So this feature a of x gets expanded into many feature functions, but when we're updating the weights based on this training example, we can skip doing the update for all of these feature functions. Okay. So what is the stochastic gradient algorithm? So for all training X and Y, then for all J, then compute the expected value of Fj of x, y prime, and then do an update Wj gets Wj plus lambda times Fjxy minus, call this just E, Fjxy minus E. So there, and as I was just saying, there are special cases where you can avoid doing these updates. And unfortunately, this is still pretty expensive. What's going to be the expensive part of this? Computing that expectation. And actually, to compute these expectations in general, you have to use an algorithm that is like the matrix algorithm that I presented. Unfortunately, I don't give that algorithm explicitly in my notes. It's something I want to add to the notes. But you can find that algorithm explicitly in the tutorials that I've provided references to. So if you look on page 24, there are listed references to 4 tutorials. And so the tutorial number 3 in particular by Rahul Gupta, he goes into detail about the matrix multiplication algorithm for computing this. And I'm sorry, I didn't understand the question.
If this one is unpublished, especially from IIT Bombay, how do you get it?
Just,
by personal contact?
yeah, no, just use your favorite search engine. Yes. I wish he'd published it. I wish I had it doesn't even have a technical report number. But if you just search for Rahul Gupta conditional random fields, it's a top hit. I think the algorithm is also given, but less explicitly, in the first 2 tutorials. Okay. Since even stochastic gradient training is expensive for conditional random fields, I want to use the last minutes to explain an alternative. This is going to be, this is section 5.1 in the notes.